So we're going to start talking now about what are called convergence tests and kind of help put this in perspective of what we've done and where we still need to go with series in AP Calculus BC. First, kind of an overview. So what I've discussed in this series of videos so far is how we build a Taylor series that will converge to a function in an unknown interval of convergence. And then we talked about how could I find a preliminary interval of convergence by using what we call the ratio test. So what we still need to know is how can we decide if a series converges when the ratio test is inconclusive? How can we find the final interval of convergence, which includes the endpoints? And then we have to end by discussing the fact that there are different types of convergence. Most of the convergence that we've been looking at is what's called absolute convergence, meaning that if I take the absolute values of all of my terms in the partial sums, and as I'm adding up the absolute values of the terms, if that converges, well, then the non-absolute values have to converge. But what happens if the absolute values of the terms don't converge? That's what we have to look into still as well. But this series of videos is looking at what are called convergence tests, which are, other than the ratio test, how can we decide if a series converges? So the one I'm going to talk about in this test is actually not a test of convergence. This is actually a test for divergence, and it's what's called the Nth Term Test. And what it is we look at the terms that are being added up, and if the limit as n goes to infinity of those terms is not 0, then the series must diverge. If the limit as n goes to infinity of those terms is 0, it actually doesn't tell us anything. It might converge, it might diverge, we don't know. So this doesn't tell me if something converges, it just tells me that something must diverge. I like this test because it is relatively quick. If it's a test that's not going to be very quick, I skip it and move on to one of the other tests. But sometimes you can look at a series and do this test very quickly. So it doesn't hurt to kind of just start with this one. So some examples of this, if I have the sum where n's going from 1 to infinity of 2n plus 1 times n minus 6 over 2n squared minus 5, well, the nth terms test says, let's look at the limit as n goes to infinity of the 2n plus 1 times n minus 6 over 2n squared minus 5. Because n is going to infinity, I can use n behavior models. So this is behaving like the limit as n goes to infinity of 2n squared would take over on top, 2n squared would take over on the bottom, and this gives me 1. So because that limit approaches 1, this series must diverge by the nth term test. So I don't even need to worry about trying any other test because it doesn't converge. I know that for certain. A second example here is if I have the sum as n goes from 1 to infinity of e to the n plus n over n factorial. If I were to do the nth term test on this, I'm looking at the limit as n goes to infinity of e to the n plus n over n factorial. Because n is going to infinity, I can use n behavior models. So that's going to be equivalent to the limit as n goes to infinity. On the top, e to the n starts to dominate. On the bottom, it's just n factorial. But then remember that as n is going towards infinity, a factorial grows faster than an exponential. So the n factorial is getting bigger faster than e to the n. So I have something getting larger and larger and larger faster on the bottom. This is approaching 0. So by the nth term test, this is inconclusive. I don't know if it diverges or not. It might diverge, it might converge. I don't know. Because it's inconclusive, I need to try a different test.